Welcome to the AI Research Roundup. I am Alex, and today we're looking at a paper from the Papers with Code trending list, published on the 5th of June, 2025. This paper introduces a new model that substantially improves an AI's ability to understand and point to objects in videos based on complex text commands. The paper is titled VideoMolmo, Spatio-Temporal Grounding Meets Pointing. So the core idea here is tackling spatio-temporal localization, which is a way of saying figuring out exactly where an object is and tracking it over time in a video. Current video models are pretty good at the tracking part, but they often lack the sophisticated reasoning to understand complex instructions. This paper introduces VideoMolmo, which cleverly splits the task. It first uses a large language model to figure out what to point at, and then uses a separate module with SAM2 to create a smooth, coherent highlight of that object across all the video frames. And for those who want to dive deeper, the authors have released the official code for this work. Right now on GitHub, you'll find the inference code, which lets you run the pre-trained model, along with setup instructions and even a sample video to try it out. The team does mention that the scripts for training and evaluation are coming soon, so that's something to keep an eye on. Alright, and this first figure really gives a perfect visual of what we're talking about. The models are given a pretty tricky command. Point to the white pigeon that has moved a little from the left to the right. You can see the results from a few different models here. The top two, Video Lisa and Video Glam, they struggle a bit, highlighting multiple birds or creating messy, scattered masks. The third model, Molmo plus SAM2, gets closer, but the mask is still a bit rough. But then you look at VideoMolmo's result at the bottom. It's much cleaner. It correctly points to the right pigeon and generates a really coherent mask that tracks it perfectly across the frames. So how does VideoMolmo achieve that really clean result? This diagram shows us the architecture. It takes in video frames and the text query, like point to the ball. A visual encoder processes the current frame and several past ones. These then go into a special temporal module using multi-head cross-attention, which is a way for the model to let the current frame's features query the past frames for important context, like how an object is moving. This enriched visual data is combined with the text and sent to the LLM, which outputs specific coordinates. Finally, those points are converted into a smooth mask using temporal mask fusion. Okay, so that architecture is designed to take in a video and text and spit out a precise point. But a model is only as good as its training data. So how do you get the thousands of perfect point annotations needed to teach it? This figure shows the clever semi-automatic pipeline the authors created. They start with existing datasets that have a ground truth mask, which is basically a perfect pre-existing outline of an object. They sample several points within that mask and use SAM2 to generate a new mask from each point. Finally, they compare all these new candidate masks to the original ground truth using a metric called intersection over union, or IOU. Intersection over union is just a score that measures how much two shapes overlap. The point that generated the mask with the highest IOU score is then selected as the perfect training label. This process gives them the high-quality point data needed to train the model effectively. Alright, so after training on that huge, carefully curated dataset, the real test is how VideoMolmo performs on tasks it has never seen before. And that's what this figure demonstrates. Its ability to generalize to what we call out-of-distribution scenarios. These are videos from specialized domains like cell tracking, autonomous driving, and robotics that were not included in its training. You can see it handles incredibly diverse and specific requests, like pointing to all the cells, identifying only the closest traffic light, or tracking a specific toy carnivore animal for a robot. This shows the model isn't just memorizing. It's really understanding the language and the visual context. So, seeing that impressive performance, the researchers wanted to dig deeper into why the model works so well. This chart zeroes in on that temporal module we discussed, the part that looks at past frames for context. The horizontal axis, L, represents the number of past frames it considers. The vertical axis is a performance score called J&F, which is a combined measure of mask overlap and boundary accuracy. You can see the score climbs steadily as the model gets more context, from 1 to 4 frames. It peaks at 4, and then dips slightly at 5, suggesting that 4 is the sweet spot for understanding motion without getting too much noise. And that optimized temporal module really pays off when we look at the bigger picture. This table compares VideoMolmo to other leading models on the task of referring video object segmentation, which is basically finding and outlining a specific object throughout a video, based only on a text description. We're looking at performance across three major benchmarks: Refer Davis 17, Refer YouTube VOS, and Mevis. Using those J and F scores we saw before, which measure mask quality, VideoMolmo consistently comes out on top. The improvement is especially dramatic on the Mevis benchmark, showing its superior ability to handle complex scenes. And that ability to handle complexity is pushed even further here on the Reason VOS benchmark. This isn't just about finding a simple object. This benchmark tests the model's ability to follow more complex, multi-step logic within the video. And looking at the results, VideoMolmo once again sets a new state-of-the-art. It scores 51.1 on that combined J and F metric we've been using, which measures mask quality. This superior performance really highlights its enhanced temporal and fine-grained reasoning abilities, proving it can handle much more nuanced requests than previous models. So it's clear that VideoMolmo represents a really significant leap forward by effectively combining spatial-temporal grounding with that pointing mechanism. The model isn't just finding objects, it's truly understanding complex, multi-step instructions within a video. This opens up exciting new possibilities for more intuitive and powerful video interaction tools. That's all we have for today. Thanks for tuning in to the AI Research Roundup. I'm Alex, and I'll see you next time.